In this video we are going to take a look at how to convert from decimal to binary and other number systems. Our goals are to convert integers to binary using tables first, and then to convert from binary to octal and hexadecimal. And then we want to develop an algorithm to convert from decimal to Radix R representation for any size integer. So let's take a look here what we want to start with. A simple way in which we could convert numbers from decimal to binary is to use a table. And we would just simply start from 0. So that's over here. So we start with 0. And then we just add 1 to it. So we have 0, 0, 0. And we add 1 to it. And so we have 0 plus 1 is 1, 0 plus 0 is 0, 0 plus 0 is 0, and so we get to the 1 here. And then we go from 1, and we add another times 1 to it. And so now we get 0, 1, 0, because actually I should maybe erase that last part here so that we do that in the right order. So we do 1 plus 1. And that is equal to 2. But 2 in the binary number system, that's equal to 0. And then here keep a 1. And then we have 0, 0, 0 plus 0 plus 1. So that gives us a 1. And 0 plus 0, that gives us a 0. So we have 2. And so on. Here is a more interesting case where we have 0, 1, 1. So we have 3, so we count 0, 1, 2, then it comes 3. And after 3, we run out of digits if we only have 2 binary digits. And so we need a third digit now. And so we take 1 plus 1 is 2, so we write a 0 here and keep a 1 over here. And then we have another 1 plus 1 is 2, we write a 0. We keep a 0 here and the carry. And then we take 1 plus 1, then we take 0 plus 0 plus 1, and that gives us the 1 here. So we go from 0, 1, 1 to 1, 0, 0. And then we add a 1, we go to 1, 0, 1, 1, 1, 0, and triple 1. So that's one way to think of doing a conversion between decimal and binary by just simply exhaustively write down all the numbers. Okay, so an interesting way of using this table also is to use it for binary to octal conversion. So if you have a binary number and we want to convert it to octal, we just partition the binary number, like this number here, for example, 1, 1, 0, 1, 0, 1, 0, 1. We partition it into parts of 3 bits, like this. And if there is, we start at the right end with that whole thing. And if there is not enough digits on the left, we just simply think of putting in a 0. And then we take the 1, 0, 1. So we go into the table here, that is 5. So that gives us the 5 here. We take 0, 1, 0. We go into the table, that gives us 2. So that's this 2 here. And then we have 0, 1, 1. That gives us this part here, so that is a 3. And so the binary representation 1, 1, 0, 1, 0, 1, 0, 1 actually converts into an octal representation of 3, 2, 5. And both of those have the same value. Okay, and then we can extend this whole idea. We can now do a table for 4 bits. And again, when we just add 1, so we take 0, 0, 0, 1, and we add that to 0, 0, 0, 0. So that gives us quite trivially 0, 0, 1. It gets more interesting when we get to, for example, 7. And we now have to add 1 to it. So now we will have quite a few carryovers. So we have 1 plus 1 is 2. That gives us a 0 and a carry. and then 1 plus 1 is another 2, 0 and the carry, and 1 plus 1 is 2, 0 and the carry, and then that goes here. So that's the transition from 0 triple 1 to 1 triple 0. So that's from 7 to 8. Okay, now once we get to 9, then the next number is going to be 10. Okay, and then comes 11, 12, 13, and 15. Because we have 4 bits here, we have a maximum of 2 to the 4 distinct numbers that we can make. So that's equal to 16. And because we start at 0, the largest number we can have is 15. And thinking of the hexadecimal number system, we actually oftentimes instead of 10 we write A, instead of 11 we write B, 12C, 13D, 14E, and 15F. And we can use this table just like we use the one with 3 bits for binary to octal conversion or vice versa. We can use this for binary to hexadecimal conversion. And for example, if we take our binary string 11010101 again, we now would partition it into pieces of 4 bits. We start at the right end and then go to the left and partition it into segments of 4 bits. And so now we have 0101. So if we go back into the table here, we find that 0101 is equal to 5, and the 1101 is equal to 13 or D, and so we get the conversion of this binary number to hexadecimal is D5, so N16 is D5, and the value of N2 is equal to the value of N16, so those represent the same quantity, just in different representations. And it's actually one of the reasons why people use hexadecimal is that when they get long binary strings, it's much more convenient to write the shorter hexadecimal ones. And so you often will have to do conversions between binary and hexadecimal. Okay, so now as we start going into larger numbers, we need a more systematic way of doing the conversion. We cannot write tables for, say, numbers with 20 bits or something like that. That would be too excessive. Now, if we go back to the formula of how we evaluate the value of a number in Radix R format, it is the sum from k equal to 0 up to capital K minus 1. So that's for a k-digit number. N sub k times r to the k, so nk is the actual digits, and as we know they are in 0, 1, 2, up to r minus 1, if it's an Radix R number. And we can rewrite that as being the sum from k equal to 1 up to capital K minus 1 of nk times r to the k. So we basically take the first member of the summation and pull it out of the summation. So that's the n0 here. So it's n0 times r to the 0. So that's just simply n0. And then we make a change of variable from so that we go from k equal to 1 up to capital K minus 1. We go from k equal to 0 up to capital K minus 2. So basically what we do here is we let k become k plus 1 in our change of variables. And so now we can write this summation here as k equal to 0 up to capital K minus 2 times n sub k plus 1 times r to the k plus 1. Okay, so we made this step here. And then, because we have here r to the k plus 1, we can pull out one r from here. So we can write this now as k equal to 0 up to capital K minus 2, n sub k plus 1 times r to the k, and then put the whole thing in parentheses, and then times r for that whole expression plus n0. So now that looks like the division algorithm. So let's actually take a look at this quickly and then go back to that formula up there. So the division algorithm says that for every pair of integers, capital N and capital T not equal to 0, there is a unique pair of integers Q and R such that N can be expressed as Q times D plus R in a unique manner. And we call the D here the divisor, Q is the quotient, and R is the remainder of the division. And the condition that is needed to make this unique is that the remainder is between 0 inclusive, and the magnitude of Q, so that's the quotient. That should not be the quotient, that should be the divisor. So let's change that here. If we can erase that thing. Okay, so now we have to take the D here. Okay, so it should be between 0 and the magnitude of the divisor. For us, the divisor is R, the radix, and we're going to use positive radixes, so the magnitude doesn't really matter. So this thing here looks exactly like what we have derived up here when we went from the V of n sub r from the original formula to the newly derived formula where we have a reduced sum. It's reduced by one member times r plus n0. And so we can, if we know this quantity here, if we know this quantity here, the divisor, and we know this quantity here, the value of nr, then we can uniquely determine this quantity here. Let's do that in a different color. We can uniquely determine this quantity here and this quantity here. And so if we know what n0 is, then we can write out the first digit, the least significant digit of our conversion of the number. And so now the next thing to observe is that we have now this summation here, and we have n0. This summation is one less than the original one was for the value of the number n sub r. And we can now continue recursively and take this and take off the first member, the k equal to 0 member of this. So we get k equal to 1 up to capital K minus 2, n sub k plus 1 times r to the k plus n1. Okay, and then we can use that change of variable again. We can reduce this summation here, or we actually not reduce, but shift it from k equal to 1 to go from k equal to 0 up to capital K minus 3, and compensate here by adding 1 to the n sub k, so it becomes n sub k plus 2 times r to the k, and pull out 1r, and so we are again back to having here a quotient and a divisor and a remainder, and now the remainder is n1. So that's the next digit that we want to compute in our conversion from decimal to some radix r number system. And so we can continue with this recursively and get n sub 2 and n sub 3 and so forth. And this is really the general method for doing a conversion from a decimal number to any radix r number of any length. The decimal number has to be an integer, but otherwise there are no constraints on that. So the theory here might seem a little overwhelming, so let's actually look at the practice of it. It's much easier than the general theory. So we're going to take now an example, and we're going to convert n sub 10, the decimal number 441, to binary. So we start out with 441, and we divide this by 2. That's our radix in this particular case. So we have r equal to 2 now. So we take 441 and we divide this by 2. And that gives us 220 plus a remainder, which is equal to 1. Okay, and that remainder, that is actually n sub 0. Okay, so we have done the first step here. We've gotten n0. Now we have the number 220 is the next one that we are working on. So we take 220 and divide it by 2. So that gives us just 110 plus a remainder of 0. And so that is remainder of 0, that's n1. Then we take 110, so we basically go here diagonally with those numbers. So 110 now becomes the new number which we divide by 2. That gives us 55. There is no remainder, or remainder of 0, so that gives us n2, the digit n2. Then we take 55, and that divided by 2 gives us 27 plus a remainder of 1. And because the remainder is 1, n3 is going to be equal to 1. And we continue this way. 27 divided by 2 is 13 plus 1. So we have another remainder of 1. Then 13 divided by 2 is 6 plus a remainder of 1. 6 divided by 2 is 3 plus a remainder of 0. And 3 divided by 2 is equal to 1 with a remainder of 1. And then 1 divided by 2 gives us 0 and a remainder of 1. And once we get the quotient here that is 0, then we are done with our conversion. We don't have to do anything more. Now the thing to remember when we do those conversions is that the LSB is actually computed first. So the first remainder that we get is n0, and the last one is the most significant bit. And so we can now just read off from the bottom to the top, and we get n2 is equal to 1, 1, 0, and then 111, and 0, 0. And it's easy to check that this is the right result. This is done down here. So we have 0, 1, 2, 3, 4, 5, 6, 7. So let's see, now we have one more. I think I forgot one of those. Then we have 0, 0, and then there is the 1 there from the n0. Okay, so we have 0, 1, 2, 3, 4, 5, 6, 7, 8. The highest power of 2 is 8 here. So it's 2 to the 8 plus 2 to the 7, and then 2 to the 5, 4, 3, and 2 to the 0. And add it together, that gives 441. Now usually we're not going to write it out in that much detail. We use a more concise notation. And it's written over here, but I'm going to do it once more so that you see the sequence of the whole thing. So we start out with our 441. And we divide that by 2, so that gives 220 and a remainder of 1. So we write the remainder here. The 220 we're going to write here. And then we divide this by 2, so that gives us 110 and the remainder of 0. And we divide that by 2, so that gives us 55 and the remainder of 0. So we have the 55 here. So we divide that by 2. And 55 divided by 2, that gives us 27 and the remainder of 1. 27 divided by 2, that gives us 13 and the remainder of 1. Then 13 divided by 2, that gives us 6, and the remainder of 1. 6 divided by 2 gives us 3, and the remainder of 0. 3 divided by 2 gives us 1, and the remainder of 1. And 1 divided by 2 gives us 0, and a remainder of 1. And so we have again this number 110111001. Again, here is the MSB, and here is the LSB. Okay, let's do the same thing now for converting to ternary, just to see that that works not just for binary but for other number systems as well. So we're taking here 441, and we divide that by 3. 441 is divisible by 3. It's actually 3 times 147, so we get the remainder of 0. Then we take 147, that's again divisible by 3, and that gives us 49, and the remainder of 0. Then 49, we go back to 48, that's divisible by 3, gives us 16, and then we have a remainder of 1. Then we have 16, that's 15 plus 1. 15 divided by 3 gives us 5. The remainder here is 1. And then 5 divided by 3 gives us a 1, and the remainder of 2. And 1 divided by 3, that gives us 0, and the remainder of 1. And so we have our number here right from the bottom, 1, 2, 1, 1, 0, 0. So that's our number, the decimal number 441, now represented in the ternary number system. It's again quite easy to see that that is correct. You just simply take here 1 times 3 to the 5 plus 2 times 3 to the 4 plus 1 times 3 to the 3 plus 1 times 3 squared. You add those all up and you actually find that this is 441. Let's continue with the conversion to octal. And here we actually have two possibilities. We can either do that direct conversion from decimal to octal, or we can make use of the fact that we have the binary representation of the number already and just convert from binary to octal. So let's do both of those. If we take the direct conversion from decimal, we have 441 divided by 8. So 440 is divisible by 8, that gives us 55, and we have a remainder of 1, so that's the least significant digit here. Then we have 55. 48 is divisible by 8 and gives us 6, and 55 minus 48 gives us 7 for the remainder. And 6 divided by 8 gives us 0, and a remainder of 6, and so we get the octal number 671. Again, we're reading it from the bottom to the top to get the most significant digit to the left. And if we go back to the binary number that we had, or the binary representation of the number that we had, that was 110111001, so we partition it into groups of 3 bits, starting from the right side, and we get 1, 7, and 6. And so we again have the number N8 equal to 671. And the check, as usual, 6 times 8 squared plus 7 times 8 plus 1 times 8 to the 0, and that is 441 again. And as the last one, we want to do the conversion from decimal 441 to hexadecimal, and we can again proceed in 2 ways. We can do the direct conversion from decimal to hexadecimal, or we can do the conversion from the binary number that we have already to hexadecimal. So 441 divided by 16 turns out to be 9 plus a remainder of 11. So 9 times 27 is 440. 9 times 27 plus 11 is 441. Okay, and then we have 27 divided by 16, that gives us 1, and the remainder of 11. And then we have 1 divided by 16 gives us 0, and the remainder of 1. So we have the number 1, 11, 9, but 11 we write, of course, in hexadecimal as B. Okay, so we have N16 is equal to 1B9. And if we do this directly from the binary number that we have already, we partition into groups of 4 bits. And at the end we have just a single 1 here, so we convert that into a 1, into not the 1 0, but into a 0 0 and a 1. So we just extend to the left with zeros. Again, we have to start on the right end with our partitioning into groups of 4, and we get 1001, that's 9, 1011, that's 11, so we write the B here, and 0001, that's equal to 1, so we get the 1B9 again. And for the check, we just take 1 times 16 squared plus 11 times 16 plus 9, and that's 441. And we note here that in general, an alternative way to obtain a binary representation of a decimal number is to actually convert first to hexadecimal, because that in general requires fewer steps. The computations are a little more complicated, but it's fewer steps. And then once we have the hexadecimal number, we can actually expand it into binary, we take the 1B9 that we just computed in the direct conversion to hexadecimal, and we expand the 9 into 1001, the B11 into 1011, and the 1 into 0001, and so we get our binary representation again of 441, which is 000, 110, 111, 001. And of course the 000 here to the left, the leading zeros, we don't really need to keep, so we could just say it's 110, 111, 001, which of course we have obtained previously in the direct conversion from decimal to binary.